your notes on kinematic curves, and we'll refer to these as your stacks of kinematic curves because you will be using the slope of one graph to predict the movement and the slope of the next graph, to predict the movement and slope of a next graph, etc., etc. So you'll literally be stacking these kinematic curves. Traditionally, the order that you will be following is a position versus time graph, which position is just another word for displacement. From the slope of that graph, that would give you meters over seconds, known as velocity versus time graph, which would give you meter per second, which would be acceleration versus time graphs. What we call kinematic curves, or look at kinematic curves, is a way to visually discuss the movement of an object. First type that we'll look at is position versus time graphs. This graph will discuss where an object moves to or does not move to based on what the slope of the graph looks like. Remember to assess the positive and negative position. Pretty important here. You want to remember, am I moving up, away from, like am I going from 1 to 2 to 3 to 4 to 5 meters? Or am I going from 5 to 4 to 3 to 2 to 1 meters? Something else that you would want to do there is look at the number values on the y-axis, because the y-axis will equal your position. In other words, your displacement. Okay, something else to keep in mind. Time is never negative. Yeah, in other words, you always want the head of the arrow to point towards the right. It'll never point towards the left, because that would imply that you went from 5, 4, 3, 2, 1 seconds. Okay, instead of going 1 second, you're this far away, 2 seconds, you're this far away, 3 seconds, you're even this much further away now. So one thing that I usually do to kind of figure out what would this graph look like is talk your way through the scenario. So you look at a graph and show that it is moving away from the starting point, because on your y-axis you can see that that slope, based on the head of the arrow, the direction that it's heading, you're increasing from 1 to 2 to 3 to 4 to 5 meters. Or are you starting at 5 meters, and as time is going on, the head of the arrow seems to be trailing down towards that 0 x-axis position. So once again, talk your way through it. What do you see? Okay, let's talk about a simple direct position versus time graph. This means that the object is moving at a constant speed. The object is moving at a constant speed in both displacement and time. So a general graph would look like, here is your displacement or position in meters, your time in seconds, therefore the title is x versus t, in other words, your y variable versus your x variable. And as time is going on, you're moving away from your starting position, 1, 2, 3, 4, 5 meters as time is ticking on, and you're doing it at a constant rate. The slope of 1, 1 is 1, of 2, 2, of 3, 3, etc. So you're always going to see that you're having a slope of 1 here. More specifically, does this graph show a constant positive velocity or a constant negative velocity? Well, how would you assess that? Once again, in physics, we don't look at positive and negative numbers, we look at direction. So which way were you headed? Are you increasing this direction or decreasing it? So your correct answer here should be A, that this is a constant positive velocity that you would see. Okay, so now let's look at direct by the square, position versus time graph. This usually means that the object is speeding up or slowing down while time is increasing. One thing that I want you to keep in mind is that slowing down does not always imply a negative slope. Because notice how I'm just saying speeding up or slowing down. Well, we're in physics, right? So if we're talking about displacement, I need to know and in what direction. Because you're speeding up in the negative direction, that would be a negative slope, right? Positive and negative. But if you were speeding up in the positive direction, then that would be a positive slope. What if you were slowing down in the negative direction? If you were slowing down in the negative direction, then eventually you would see a positive slope. Now, what I just said kind of entails your acceleration versus time graphs, but what I really want to embed here is that you don't necessarily always say that if an object's speeding up, you will be seeing a positive slope all the time. That is not true. Now, when we talk about our position versus time graphs, yeah, you'll see that. Okay, so let's draw what this looks like, speeding up. So I'm going to break this a little bit here and say that you are speeding up and it is a displacement versus time graph. So think about like the entrance ramp to like 77 North. You're heading up towards Cleveland for the day. So you jump on like at Portage or whatever, and you're hitting the accelerator, right? You look at the speedometer and it's not staying at a constant velocity. You're increasing your velocity as time goes on. Well, since you're increasing your velocity as time goes on, you should be seeing this kind of a relationship. So this would be speeding up. Whereas, okay, cruise control was set, you traveled your whatever miles. Oh, here's my exit that I want. So let's show what slowing down looks like now. So you are traveling, but your time is still going on, but you're not going to be traveling as great as you were when you were traveling faster. So you're traveling a lot of area in a short amount of time, and then not so much area, and time almost seems to come to a still, i.e. you're about to hit that red light. In other words, you're going to be stopped at 5 meters away for a couple of seconds or whatnot. So the left-hand side here, you can see speeding up. On the right-hand side, you can see slowing down. These are both in the positive direction. Okay guys, moving along. A straight line, position versus time graph. This means that the object is at rest at a given placement as time increases. So once again, titling and labeling our axes. Let's say that you started 3 meters and you were going to travel for 5 seconds. And on your mark, get set, go. You didn't move anywhere, okay? At 1 second, you were at 3 meters. At 2 seconds, you're still at 3 meters. At 3 seconds, 3 meters. 4 seconds, 3 meters. 5 seconds, 3 meters. So in other words, you were at rest. Okay, we don't want to say stopped. Be physicist here. We're going to say the object is at rest for 5 seconds at the 3 meter mark. So a flat line, a straight line on a displacement versus time graph or position versus time graph implies that the object was at rest. Let me backtrack real quick. If you see a direct by the square, then that means, or direct by the square root, then that means that the object was either speeding up or slowing down. If you see a simple direct, that means that the object was moving at a constant velocity. Not saying that you should memorize them that way, but just look for trends. Okay, so let's try the graphing this example. An object starts at rest and moves at a constant speed for 10 seconds, in which the object has moved 10 meters. All of a sudden, the object comes to a stop and stays at rest for 5 more seconds. Okay. Displacement versus time. Nice increments here. We are going to go 10 meters. So 2, 4, 6, 8, 10 meters. And we're going to be doing this for 15 seconds. So whatever, 2, 4, 6, 8, 10, 12, 14, 16 seconds. All right, looks pretty good. So it says an object starts at rest and moves at a constant speed for 10 seconds. So, in which the object has moved 10 meters. So at 10 meters and 10 seconds, we are moving at a constant velocity. Remember, a constant velocity implies a simple direct relationship when you're building position time graphs. So here you go. This is exactly what you should be seeing so far. All right, let's continue reading on. It says, all of a sudden the object comes to a stop and stays at rest for 5 more seconds. So 10, 12, 14, 15 would be about right here. And it's staying at rest, so it's not moving any more additional meters up, i.e. y-axis. So this is what your graph should be looking like. All right, moving right along. Try this one. A car is stopped at a red light 5 meters up the road for 6 seconds. When the light turns green, the car speeds up to a placement of 15 meters up the road. At this point, the car has been traveling for a grand total of 10 seconds. Rule number 1, guys. Title your guys being graphs, and label your axes with variable and units. Once again, your variables are just written there, your units are put into parentheses. Okay, 5 meters up the road for 6 seconds, 15 meters up the road, 10 seconds. So 2, 4, 6, 8, 10, 12, 14, 16. And let's see here, our time is for 10 seconds. So 2, 4, 6, 8, 10. Car stopped at a red light 5 meters up the road for 6 seconds. So here's 5 meters, and here is 6 seconds. So if you're just stopped up the road, okay, it's a position time graph, and that means that as time was going on, I was standing still. I was not moving anywhere. So after those initial 6 seconds, I'm still at 5 meters up the road. When the light turns green, the car speeds up to a placement of 15 meters up the road. At this point, it has been traveling for 10 seconds. So here is our 15 meters, and here is our 10 seconds. So you are speeding up. So that's what that part of the graph should look like. Okay, guys. So standing still, at rest, and speeding up for that section right there. Next one, velocity versus time graphs. For velocity versus time graphs, what you're going to do is show that an object has sped up or has slowed down, but really honestly, these words are used with acceleration time graphs, not so much for velocity time graphs. You are at rest or at a constant speed. Something else I would love to interject here is that crossing over x-axis implies change in direction. So you throw your pencil up in the air and it comes back down to you. Eventually, if you would graph that, you would see that you crossed over the x-axis because it changed directions. So a change in direction is going to be implied by a crossing over of the x-axis on your on your velocity versus time graphs. The slope of a velocity versus time graph indicates acceleration as well. Okay, so we're going to draw some here. The constant speed, for instance. Constant speed on a velocity versus time graph. The first thing I would like you to notice is that with velocity time graphs, we're always going to show that we have the potential crossing over the x-axis. So draw your template of your graph this way, always, always, if you're talking about a velocity time graph. Okay, so if you're moving at a constant speed and I would draw this in, really what you guys should write down is that you moved at a constant what? You moved at a constant positive speed. Whereas if we drew this in, that's what you would see. Okay, at rest then would just simply show you that you were stopped at a red light, and if you're stopped at a red light, then you have no velocity. So you would travel right on your x-axis. All right, so that's it for this video. Click on to the next one and we will continue velocity and also talk about acceleration graphs.